Hello and welcome to AI for Developers. I'm AI Educator Talking Bot. Today's lesson is titled Why I Rewrote My Trading Engine in Rust. Latency, safety and concurrency. My initial trading engine, while functional, suffered from Python's inherent limitations. GIL contention, garbage collection pauses, and type-related runtime errors. These issues severely hampered performance in latency-sensitive DeFi environments. We're talking about the difference between filling orders at optimal prices and experiencing unacceptable slippage due to microsecond delays. Version 1 was hitting 5 milliseconds mean latency. Unacceptable. Rust offers a compelling alternative. Its zero-cost abstractions, ownership model, and fearless concurrency provide the necessary tools to build a low-latency, memory-safe, and highly parallel trading engine. The key is minimizing garbage collection overhead, a major bottleneck in languages like Python and Go. Results show Rust can reduce execution latency significantly, as demonstrated by the drop from 89 microseconds to 12 in some real-world examples, directly impacting profitability. Rust also eliminates data races at compile time. The new architecture incorporates real-time data feeds, market data, order book snapshots, ingested via Aaron and processed by a customized agentic loop written in Rust. This loop handles order placement, risk management, and position tracking. We implemented a lock-free message queue for inter-thread communication. This design allows for parallel processing of market data and faster order execution, directly improving fill rates. Leveraging Rust's async and Tokyo libraries enables highly concurrent execution without the overhead of traditional threading. We achieve this by dividing the trading strategy into independent tasks that can be executed concurrently. These tasks include signal generation, order sizing, and risk assessment. We can spawn 1,000 async tasks without performance degradation, a stark contrast to thread-based approaches in other languages. Rust's ownership system and type system catch potential errors at compile time, preventing runtime crashes and data corruption. This is crucial for maintaining the integrity of trading positions and preventing erroneous order execution. We leverage these features to implement robust risk checks and limit orders that automatically trigger under adverse market conditions. We explicitly handle potential errors during API calls, such as order rejection or network failures, ensuring a resilient system. To enhance decision-making, we integrated a private retrieval augmented generation (RAG) system trained on our proprietary research and market data. This system provides real-time insights into market sentiment, news events, and potential alpha opportunities. The RAG system is also written in Rust for low latency and seamless integration with the trading engine. We're using FAISS for vector similarity search, ensuring fast retrieval of relevant information from the knowledge base. The rewritten engine achieved a significant reduction in average execution latency, dropping from 5 milliseconds to under 500 microseconds. This improvement directly translates to increased profitability, improved Sharp ratio, and reduced risk of ruin. Backtesting results show a 2x increase in annualized returns compared to the Python-based engine. We continuously monitor performance metrics and conduct regression testing to ensure optimal performance. The Rust trading engine is deployed using Docker containers and orchestrated with Kubernetes. This allows for easy scaling and management of the system across multiple servers. We use Prometheus and Grafana for monitoring performance metrics and identifying potential bottlenecks. We're working on expanding our server infrastructure to handle increased trading volume and market volatility. The containerized approach ensures consistent performance across different environments. Thanks for watching. If you found this helpful, make sure to subscribe to our channel and hit the like button.